2600 BC, ancient Egypt. How were the pyramids built? That's a question that people have asked all these years. Here almost 5,000 years later. We're still wondering how those pyramids were built. But if you look at some of the historical information, some of the archaeological data that's been recovered, there seems to be two predominant ideas on how the pyramids may have been built by human hands. One was to use what can best be described as a wheel with a square block in the center, and then riding inside the square block was essentially a bearing assembly. It was a wooden block that has what could very well be the first self-lubricating sleeve bearing ever registered in history. It appears as though they may have used simple pounded copper and lined the inside of the wood block that's set within the stone block that then set within the rolling wheel. And then lots of people would then pull by rope up these long ramps. So it could very well be that that was really one of the first plain bearings ever represented in archaeology. The other type of method that people seem to believe may have happened was the use of a sled. This sled was made out of wood, and it rode on wood tracks. They would take each stone, again using huge amounts of manpower and ropes, to pull these large blocks along these sledded tracks. And there are some that say that water was used to lubricate the wood. Others have said that animal fats were used. But either way, this could very well be representative of the first linear bearing. So here we have two ideas on how the pyramids were built. Both conceptually had the whole concept of plain bearings all figured out. But then there's others that believe that the pyramids weren't built by man, but in fact were built by the aliens. So I guess we'll never know. We'll have to just speculate and believe that somehow they were built, and somehow 5,000 years later they're still standing. Let's jump a bit to the 1st century AD. You may have heard the stories of an infamous Roman emperor named Caligula. Caligula had a lot of very strange ideas on how life was supposed to be lived, but one thing he did know was marine architecture. And he ordered his marine architects to build for him what was at that time the largest ship ever built, and even by today's standards is very, very interesting as far as dimensions. It was over 350 feet long and 60 feet wide, stood 6 stories tall, and it was basically a giant party barge that set out in the middle of Lake Nemi in Italy. But what makes it even more interesting is some technology they found on board. There's a museum now close to Lake Nemi where they recovered a lot of the remains of the ship, and found that in the bottom they had a turntable, and on this turntable allegedly stood a very large statue of Diana, the goddess who was the most popular back in those times. If you look at the picture, you can see that this is a classic thrust bearing, a large plate with what appeared to be balls, and that made it very simple for this very large wooden turntable to rotate on its own axis. So here we had Caligula, of all people, using a technology that is still used today and is classified as a bearing. Whether it's a plain bearing or a rotating bearing, it's still a bearing. So let's jump ahead a little bit further, the 1500s and the 1600s. There are drawings that show Leonardo da Vinci's first concept for the idea of a rotating bearing using balls and separators. Shortly thereafter, Galileo came up with the same concept, but his was a more of a caged ball. But here we had, again, indications long before practical application of bearing materials being utilized in simple designs. Now we jump way ahead. We jump into the late 1800s. And there were two gentlemen that did some interesting things with very little technology that was known at the time. Isaac Babbitt, who was a goldsmith in Massachusetts, introduced a product that was a simple metallic plain bearing, and today it's still used, and today it's still named after him. It's a Babbitt bearing. This is basically just a lead or tin bearing that is poured into place and is still very popular in a lot of large industrial applications. The other gentleman that is probably best known as being the first of the non-metallic materials was a fellow named Leo Baekeland. And Leo Baekeland discovered a polymeric material that was based on phenyl formaldehyde. Most of the world came to know of it as phenolic. And then later in the 20th century, we all learned of the name Bakelite, which is today still a common material for decorative products and even things like knobs on stoves. So here we have two gentlemen, late 1800s, early 1900s, who were very influential in the whole concept of plain bearings, one metallic, one non-metallic. And moving into the 20th century, everything changed. Hi, I'm Dave Bearing, Technical Director here at TriStar, and welcome to TriStar's video on plain bearings. And specifically, this video is designed to coincide with the release of our new white paper on plain bearing design and the concepts, the materials, and just what plain bearings are all about. This is a very detailed and I think a very concise recap of the whole technology as it stands today. And so this video is really meant to introduce you to where we are today, where we've come over the last 100 years. I think we all agree, and I think history proves that the 100 years of the 20th century, there was more technology advances than in history, in all of mankind. If you think about the fact that we went from our first manned flight to landing on the moon in just over 60 years, it's pretty phenomenal. You know, somebody figured out how to take silica sand and turn it into a circuit board. That's phenomenal. I mean, all of these things happened in the 20th century, and along with that came the development of virtually every plastic material we have even today. There's been very little in terms of new polymer technology, and where things have changed has been how we're using those polymers, how we're manipulating those polymers to do more and better things. There's thousands of materials out there, and so our thought is that we want to kind of encapsulate in terms of where these polymers can be used as plastics, and just to give you some basic guidelines on what plastic bearings are all about. So let's take a look at some of the basic parameters. First of all, the advantages of self-lubricating materials over metal bearings. I don't know if you've had a chance to watch our 4-part series on why metal bearings fail. Hopefully you have, but when you compare metal bearings to the advantages of a self-lubricating bearings, they're pretty numerous. First of all, self-lubricating bearings, low or no maintenance. Your cost savings in operations can be dramatic, depending on the type of lubrication and the amount of manpower you have to use to lubricate those metal bearings. No grease, so you're eliminating the collection of contamination, you're eliminating the disposal cost of getting rid of those greases, and just the manpower to keep things clean. High performance. There's just a broad chemical and temperature availability now with plastics. We have plastics that will go from cryogenic temperatures to close to 1,000 degrees. So we cover a very broad spectrum. The whole pH scale can be covered with plastic bearings. Lightweight. Some of the plastic materials that are out there now are 7-to-1 weight to strength ratio compared to metals. We have airplanes now, the 787 from Boeing, virtually all plastic. It's a composite, but it's virtually all plastic, and very lightweight as a result. Corrosion and rust resistance. And one of the failures of metal bearings is corrosion, and that can come from a lot of different sources if you watched our videos. Sanitary compliance. More and more applications now in food processing, food packaging, pharmaceuticals require no grease. They need materials that are going to be clean, sanitary, and we have a variety of materials that can offer that. And then finally, flexible design options. These materials can all function in virtually any condition. And then from the standpoint of dynamics, it's linear, oscillating, rotary. We have materials that will function in all those different applications. So what's the next thing that we want to look at then? There are a number of things that we start with when we're talking about plain bearing design. So let's take a look at the key criteria for designing with plain bearings. First of all, when we're designing a plastic bearing, we have to first define the material, and that's the challenge, is finding the right material to fit the application. So the things that we want to look at in terms of properties are elastic behavior, impact strength, thermal properties, the tensile, compressive, and flex properties, the elongation or deflection under load, hardness, dielectric values if that's something that's of concern, flammability ratings, and what's the friction and wear properties of the material. And then finally, one of the key factors of utilizing a polymer in a plain bearing is what's its PV rating. So how do we next determine what those mechanical factors are? First thing we have to do is determine the load, which is our P. This is expressed as PSI, and so it's important for us to understand what the true load on that bearing is going to be. We have materials that will only work up to 800-900 psi, and we have other materials that work up to 50,000-60,000 psi. So it's very important for us to understand what the load conditions are. Second, what is your speed, your V in RPM or feet per minute? Once we understand what your velocity is, that now either eliminates or increases the potential for a plastic material to be used. We always have to consider what the thermal properties are of a material, because speed generates heat, and heat generates plastic failure. So we always have to be aware of what's going on in terms of the speed. Thirdly, we need to know what those combined numbers are. What is the P value times the V value? Because all plastic bearing materials are going to have to fit within three very distinctive categories: P, V, and then the combined PV. Fourth, what is the normal operating temperature? You know, all plastic materials have limitations based on what their normal operating temperature capacity is. So we need to know what the normal operating temperature is, day to day, 24/7, or if it's just intermittent. Add to that, what are the maximum and minimum operating temperatures? Because now we need to determine what the potential is for press fit loss or close in, depending on whether there's cold temperatures involved, there's hot temperatures involved. We don't want to design the bearing so that it seizes up on the shaft or possibly drops out of the housing because it loses its press fit. And then finally, what's the operating environment? Is it wet? Is it dry? Is it dirty? Is it grimy? Is it dusty? What kind of chemicals are involved, if any? Do you require clean room conditions? Are there regulatory conditions you have to meet, like FDA or USDA? All of these things come into play as we go through this selection process. Now, some of the materials that we offer at TriStar are certainly the most common and predominant materials in the world of plastic plain bearings. Our most popular materials are Rulon, which is a family of self-lubricating PTFE-based materials. Rulon has been around since the 50s and is certainly the best known of the filled polymer or filled PTFE bearings. And we have literally over 300 materials in the books, but about 15, 16 materials can solve the majority of the problems we deal with every day. Rulon materials would be applications where you've either got temperature extremes, chemistries that will not work with other polymers, or perhaps some specific application requirements for very, very low friction. The Rulons do offer extremely low friction properties. Our CJ and FCJ, these are a family of filament wound high load materials. They are very low friction, and they're really meant for primarily oscillating or high load rotary applications, and they offer the user a simple drop-in replacement for bronze bushings, and in some cases we can even replace rolling element bushings as well. Ultracomp is a family of laminate wound bearings. These are extreme high load conditions, primarily oscillating low speed, but these are materials that are designed for both wet and dry. We have marine qualifications on one of our UC materials, so it's a very broad application, primarily outdoors, I would say, but places where you've got a lot of lift and tilt, heavy loads, where you want to replace bronze, or even in some cases you can replace hardened steel bushings. Our Tri-Steel product. The Tri-Steels are a family of metal back rolled bearings. These are products that have a number of different polymer liners. Some of these products can go to very high PVs with and without lubrication, and it's a simple, cost-effective drop-in design where if you need, again, primarily oscillating high load applications, the Tri-Steel family is a good, simple way to solve bearing problems. HPM, or high performance materials, these are products that are generally going to be higher cost, but they're also materials that are going to be products that are in the 400 plus Fahrenheit degree applications. Again, chemical applications, places where you need good thermal stability, good physical properties. The high performance materials fall into that category and really run the gamut of product cross section. Engineering grades of materials, these are the ones that are probably more well known in terms of our daily consumer goods. The Delrons or acetyls, nylons, both cast and extruded nylons, polyesters, PBT. These are products that are basically in the 200 degree Fahrenheit range and below, but very good for those types of applications, and certainly a long history of use. And then finally, Ultraflon, which is TriStar's own family of custom components and custom materials. These are products where if we need to manipulate existing resins or do something special for an application, our Ultraflon family is really suited for that. So let's just do a quick review of what we just talked about. The Rulons, again, a family of PTFE-based materials with a variety of fillers and additives. These are the 12 that are the most predominant, and I won't get into every one of them, but each one of these has a grouping of applications. Some of them cross over, but Rulon LR, J, and 641 certainly the most predominant in the market. But again, you can see we have materials that have been geared for specific applications, and if you look on our website, you'll see a lot of resources that you can go to learn more about specifically where you can use the Rulons. Our CJs and FCJs, again, we're talking about a high load self-lubricating material. These are materials with compressive strengths up to 60,000 psi, very low coefficients of frictions, a variety of speeds, zero water absorption, and a temperature range from cryogenics up to about 335 degrees Fahrenheit. Ultraflon, very similar to the CJ, FCJ, but it's a laminate wound. We use lubricant additives in the resin like PTFE, graphite, and moly. These again are good for service in wet and dry environments. Compressive strengths up to 55,000 psi, very low swell, and temperatures of cryo to 325 Fahrenheit. Our Tri-Steels, again, family of metal back bearings. Pretty simple, 80,000 PV dry on some of the liners and 2 million with lubrication. So again, we've got a lot of resources you can refer to. Our HPM materials, these materials would be things like Keytron Peak, the Tektron HPV, Torlon, Selazol, polyamides like Vespel and Meldon, and then your engineering grades, the nylons, acetyls, PET, PBT, and of course UHMW, which is a great go-to material if you're in a very difficult abrasive environment. And then again, our Ultraflon family of materials. So that's a very quick recap of the types of materials that are categorized in the plain bearing world. The bottom line that you have to remember with these materials, as always, is these are all self-lubricating. There's a variety of temperature and chemical possibilities. Low cost compared to long-term usage of metal bearings that require lubrication and maintenance. All of these things come into play as you go through the process of determining which of these materials really suits your applications. We hope that you'll go to our resource location again and look at some of the other things that we offer. We certainly would like you to read our new white paper on plain bearing design. I think you'll find it to be very informative, and it kind of again encapsulates all the things that we think are necessary for you to understand as you consider plastic plain bearings. Thanks again for watching. We hope this is of value to you, and we look forward to seeing you again on another video.